All right, rule number 3. If we find a sedimentary rock in a rock layer, we can assume that the fragments or the sediments that make up that sedimentary rock have to be older than the rock itself. And this is kind of common sense. This is a conglomerate rock, so whatever rocks make up that conglomerate, those rocks have to be older than the conglomerate itself because it's made up of fragments or sediments. Those sediments are already formed or weathered and broken down, so now we know that this is made up of rocks that were already formed. So it's a law of inclusion, they really call it, but no matter what, the rocks in a conglomerate or any sedimentary rock are older than the rock itself. Next, intrusions are always younger than the rock it cuts through. Igneous intrusions expose layers to contact metamorphism. Probably should have explained this first, but an intrusion happens when you have layers of sedimentary rock already existing and magma kind of burns its way through the layers and in the process affects the layers through contact metamorphism, but also cools and solidifies. So this is what it would look like in what we've been dealing with. This is a igneous intrusion right there. That's showing igneous rock. I know it's igneous rock because of the symbol. That symbol is not in your reference table. Those like sideways V's, not in your reference table. It's always a sign of igneous intrusion. So magma kind of channeled its way up, burned its way through these rocks, and solidified. Solidification turns it into igneous rock. In the process, contact metamorphism occurred. I know it's contact metamorphism because these little dashes along here and along here, usually there's a map key. Those are meant to show the process of contact metamorphism. So let's try to piece this together in terms of sequencing. So we know, based on everything we've been doing, law of horizontality and law of superposition, the deposition of E, this limestone, had to take place first. Next, had to be this deposition of shale. Now here's where things get interesting. The next event had to be this intrusion C. Why? Because it cuts through layer D and E. D and E had to be there first for this intrusion to kind of burn its way through. Then comes layer B, then layer A. This whole thing got uplifted and exposed to weathering and erosion. So just to cut back to that intrusion process, I know it's older than layers B and A because it has no effect on B and A. There's no contact metamorphism of B, and it didn't cut through B or A. So I know that C was already laid down and solidified before B and A came after. Okay? Just a little bit more about the contact metamorphism part. If I asked you what kind of rock would exist right here at X, you should be able to tell me. Now, I know you can't tell me right away, but if I gave you a reference table and told you to look, what would be the type of metamorphic rock found at X? Well, we know that the map symbol that we have here is shale. Okay? That's shale. Metamorphism of shale would turn some of that shale into the rock slate. Moving right along, we're up to Rule 5. Faults, tilts, and folds are all younger than the rocks they cut through. Rocks have to be laid down first before they can be tilted, folded, or faulted. I actually already talked about this rule in a previous cross-section. I know they're starting to look the same, but this is what I mean. So here's our sequence. We first have the deposition of limestone here. Then we have the deposition of this shale, which is the same on both sides. Then the deposition of this sandstone. Then the deposition of this conglomerate. Then we have a deposition of limestone. And then siltstone. Even though it's on the left, it could have been erased by weathering and erosion, but we know that it's still something that was deposited. Now, there is this fault here. I know that that fault came after all of those layers were laid down because it affects all 6 layers. All 6 layers show the movement of a fault, this shifting. So that means these layers were all laid down horizontally in a nice, organized pattern, and then faulting happened and shifted them so they no longer match up horizontally because it affected all of them. But this intrusion happened after all this stuff. So we had weathering and erosion after uplift, and once they were all raised above, then came the contact metamorphism. So after the weathering and erosion, right, these layers were lifted out of the ocean or whatever they were in and exposed. Then came this igneous intrusion here, because it cuts through all the layers, most of them, and it cuts through the fault. That fault was down and happened first. These layers are all shifted and raised out of the ocean or sea that they were in. And then came the intrusion, because the intrusion cuts through the fault. All right, rule number 6. Uplifting followed by weathering and erosion and then sinking create unconformities. Unconformities are layers missing from the rock record. An unconformity is like pages missing from a book. If I gave you a book and told you to read it, but I ripped out the middle, you had the beginning, you had the end, but you missed the meat of the story, you'd be pretty confused. So an unconformity is really exactly that in geologic history. Something happened to erase the middle. You can sometimes see unconformities referred to as subsidence, which really refers to layers being sunk, right? Subsidence. So layers are basically laid down, uplifted, weathered and eroded, but then sunk back down and then added to. So it's like double weathering and erosion event. Always spot an unconformity by a squiggly or wavy dark line. So spot the unconformity. And let's try to put this together. Our first geologic event will be the deposition of layer G. It's at the bottom. Then we would have the deposition of layer F, then the deposition of layer E, then D, then C. Now, what happened next? Well, it looks like G, F, E, D, C, and H is still part of D, look like they're all folded. So folding happened, right? There's this waviness to them, like an accordion. Next, these layers were lifted. Usually folding, tilting, faulting are followed by uplifting. And then they were weathered and eroded. Weathered and eroded so much that we have this unconformity. So we know that after weathering and erosion, sometime later, this whole area got sunk back down at the bottom of an ocean or a sea, and a new layer was added, and that was the deposition of layer B, limestone. And then there would be the deposition of layer A. And then finally, the only reason we can see it is because it was uplifted out of the ocean or sea again, only to be weathered and eroded finally. So just to compare the two, the top layer is not an unconformity because it's not buried. It's exposed at the surface of the earth. Only buried erosional surfaces are considered unconformities. So the blue line here is buried. It's underneath layer B. So that's why it's an unconformity, because it's not conforming. It's not following the pattern, the sequence. Something's missing. And it's because this area was lifted out of the water at one time and layers were erased because of erosion and weathering. Okay, so we went through all the rules. We went through everything that you need to keep in mind. And I know it's a lot, but that's the great thing about video, is that you can always go back. This is probably one of the hardest sequences that I've ever seen given on the regions. So here's what I'm going to ask you to do. I want you to look at this, and I put one of these in Google Classroom for you to look at, and I want you to do your best to try to sequence these events from beginning to end, from the earliest event to the last event. Take your time with it. If you do it correctly, meaning you get 100% the right sequence of events, you can earn 3 points on our next test. So bring your answer with you through Google Classroom, and you can submit it there. That's it for now. Thanks for watching.